Let's talk about electric potential energy between two charges. Suppose we have one charge that is a positive charge and another charge that is a negative charge. And let's suppose that these two charges are separated by a distance r between them. Being opposite charges, they exert a Coulomb force of attraction between each other. This Coulomb force of attraction acts on the straight line that connects these two charges, and it is equal in magnitude on each charge, but opposite in direction because it's from the same interaction. Because the Coulomb force of interaction is a conservative force, these two charges share an electric potential energy. And that electric potential energy is directly proportional to the product of the charges and inversely proportional to the distance between them. So what does it mean that they store electric potential energy, or that they store potential energy? So what does it mean that these charges store energy? Electric potential energy has the ability to transform into other forms of energy, namely kinetic energy. In this diagram, you see that we have these two opposite charges, and so two opposite charges attract, and if we were to let these two objects go, they would be attracted to each other, and if they started off with an initial speed of 0, after a short period of time, these two charges would have a speed of greater than 0. The potential energy that was stored in the relative position was transformed into kinetic energy, that is the energy of relative motion. And that's because the distance between the charges was allowed to change. If you change the distance between these two charges, you will change their potential energy. And if you change their potential energy, you will end up changing their kinetic energy in the absence of non-conservative forces. So potential energy is the energy of that relative position that gives a system of particles the ability to use other forms of energy. Well, let's look at a single particle now. Let's take that positive charge. You know that the Coulomb force between two charges, between 2 point charges, is communicated by the electric field of those two charges. The electric field of this positive charge points radially away. So if we were to put a negative charge in the field of this positive charge, then that negative charge would experience a Coulomb force of attraction based off of its position, its relative position in the positive charge's electric field. For now, let's assume the negative charge is small enough such that it doesn't disrupt the overall field significantly. So the electric field of the positive charge is responsible for accelerating the negative charge in the presence of this conservative electric field. The electric field is a conservative field, leading to the electric force being a conservative force. Well, what does this mean? Again, being a conservative field, we know that these two charges share a potential energy. That potential energy, remember, is defined by a change between two locations, which is equal to minus the work done in moving a charge between 2 points. Now, in this situation, the potential energy, any changes, is due to the electric field, where Q is Q is the charge that is placed in the field due to, in this situation, the positive charge. Okay, so if we place another charge in the field of this positive charge, they would experience a conservative force, which means that we are able to store potential energy by the field doing work on this negative charge we placed in the field. Okay, so I think we got that. We got that two charges share electric potential energy, giving them the ability to do work, for giving the fields the ability to do work to change the potential energy into other forms of energy. What if we remove one of the charges? What is the electric field's ability to have this particle, this positive particle, share potential energy with another particle? Well, this particle still has an electric field. It doesn't lose its ability to store energy as long as there can be another charge in its presence. But there has to be a way for us to qualitatively measure this electric field's ability to store energy in the form of potential energy with another charge. So this electric field must have the ability to share potential energy in the presence of another charge. This leads us to electric potential. Electric potential is the measure of the ability of an electric field to give potential energy to a charge placed within it. So this electric field inherently has electric potential. It inherently has the ability to give potential energy to another charge. And how we measure that is by saying that electric potential, we use the variable capital V to represent electric potential, and we will define electric potential as electric potential energy per unit charge. What this means is if we place a charge Q prime in this electric field, this charge Q prime will have electric potential energy that would just simply be given by the product of its charge times the electric potential of this electric field. This electric field has given charge Q prime potential energy. And remember, that potential energy is an energy of relative position. So where this charge is in the electric field, for example, if we move this charge to another location in the electric field, it may have a different value of electric potential energy. And that value is based off of the electric field's potential, its potential for giving that charge Q prime potential energy. Well, let's look at the electric potential for a point charge. In looking at the electric potential for a point charge, since electric potential, and again, this expression V is defined as electric potential. So in having an electric potential in an electric field, we are able to give another charge potential energy. If we look at the electric potential due to a point charge, and we know it's defined based off of the electric potential energy per unit charge, well, we just have to look at the electric potential energy that that point charge would have with another point charge. So in this case, Q, and I'll label our charge in the middle over here, Q. So the electric potential energy is directly proportional to the product of the charges, Q and Q prime, over the distance between them. So let's label this distance here. This distance is a distance of r. And then this is divided by the charge that we place in the electric field. So these two charges cancel, and we get that the electric potential due to a single point charge is equal to kq over r for a point charge.